Next up, we have Michael Rosenberg, who is a PhD candidate from University of Maryland, talking about a new SNARK that is horizontally scalable.
So today I'm presenting HEKATON, a scalable zkSNARK prover. This is joint work with Ian Myers of the University of Maryland, Pratyush Mishra and Tushar Mapuri of the University of Pennsylvania. I am Michael Rosenberg. I'm at the University of Maryland. I'm also a maintainer of the Curve 25519 Dalek crates and the other Dalek crates. If you're interested in paying me for that work, please talk to me after. So I have to do this at the same time. So zkSNARK, very quickly, because I assume a lot of you know this, has to have three properties. It should have proof of knowledge, meaning that it should convince someone that this is not synced. It should convince someone that the prover knows something, specifically a predicate P over a public value and also a hidden value called the witness. It should also have zero knowledge, meaning that the proof doesn't reveal anything about the witness. And it should have succinctness, meaning that a proof is concretely fast to verify. I'll just highlight two things about the predicate P because we'll need it. Firstly, P's an arithmetic circuit. That is it's a fixed depth computation using additions and multiplications. The circuit's made up of gates and wires. Secondly, every arithmetic circuit is represented using a structured reference string. That is, that the prover uses to construct the proof. This can be shared across different proofs depending on whether it's universal setup, but everyone has an SRS. Oh, sorry. And I'm fully confused. Okay. So what do we want to use zkSNARKs for specifically? So in the context of cryptocurrencies, it's often pretty small computations, like showing the existence of sufficient funds. But there are uses for larger computations as well. So there's matching algorithms for liver transplants. There's validity of a machine learning model's output. There's also proving an image that has not been modified beyond cropping or blurring or other basic operations. Also proving that a cryptographic key directory hasn't been modified except for the allowed update operations. All of these are computations over private data that have hundreds or thousands of inputs, and they can have huge consequences if they're tampered with. So efficient auditability is certainly a valuable property here. Unfortunately, simply throwing a zkSNARK at the problem doesn't quite work due to scaling issues. So previous work, DZIC, which is essentially distributed Groth16 calculation, relies heavily on internode communication for finite field, for fast Fourier transforms. Divergo is only defined to support fully uniform computations, so heterogeneous computations aren't permitted. And Pianist has an SRS that scales with the size of the total size of the circuit, which can get to be very large. There's also IVC solutions, but IVC also requires internode communication and can be slower because it relies on some recursion arguments, although that's changing. So our motivating question here is, how do you parallelize a zkSNARK prover? How far can you get? So we present the HEKATON distributed zkSNARK. The scheme has a divide and aggregate structure. That is, you divide up the circuit, i.e. partition it, into subcircuits. You prove the individual parts, and then you aggregate the proofs. The scheme is embarrassingly parallel, with no map reduce or internode communication necessary. The scheme also has cheap read-only memory accessible to the entire circuit. And the scheme has sublinear SRS size as long as there's enough repeated subcircuits. We implemented and benchmarked HEKATON and achieved a new proving record of 2 to the 35, or about 34 billion constraints. And we did this in 17 minutes on a university compute cluster. All right, let's get an overview on the divide and aggregate construction. So we begin with an arithmetic circuit, and we divide it into subcircuits. So as you can see, some subcircuits still communicate with each other. We'll call the wires that are shared between two subcircuits a shared wire. The next step is to compute a Groth16 proof for each individual subcircuit. This is done in parallel and can be farmed out to worker machines in a cluster. And then the last step is aggregating the proofs into a larger proof using an inner pairing proof that we've optimized for our specific use case, or this could be reasonably done using other aggregation schemes. So since the Groth16 prover is by far the most costly part of this entire process, and because it's done in parallel, we should expect to see significant speedups for partitionable circuits. So this is great, but the details are important. We've split up a circuit into subcircuits, but they're not totally independent, right? They have these shared wires in between them. So to make sure that our proofs are still sound, we have to make sure that the output of one of those subcircuits actually does equal the input of the other subcircuit, right? Otherwise, you can just modify whatever values in between and make it say whatever you want. So how do we get that? So since shared wire accesses are known in advance and do not change, this is equivalently a problem of achieving globally accessible read-only memory for a zkSNARK prover. In other words, this is a ROM problem. So the way proving should work in this setup is to simply calculate all of the shared wire values, stick them in ROM, give each subcircuit prover access to that ROM, let them prove the subcircuit, and then aggregate the results as before. Of course, this kicks the bucket down the road a little bit because the next question is, how do you do a ROM in a zkSNARK? This can get expensive. So the obvious way to do it is using a Merkle tree, where you put all the memory values as leaves in the Merkle tree, and then you use the root of the tree as the public input to all of the individual subcircuits. Unfortunately, this is kind of expensive. This is 300 log R constraints, where R is the number of reads. So this doesn't really scale well, especially if you might be doing a lot of memory operations. So we have to build a ROM mechanism that is cheap and also distributes nicely. So for this, we turn to permutation argument-based memory constructions from some older work that's been used in MPCs and other SNARKs like Planck to do memory. So we're going to get into the weeds a little bit. We let T be the trace of all the shared wires used by the entire circuit in the order that they're used. From here on, we can refer to abstract processes that make ROM read calls. So we'll say process and trace rather than subcircuit and shared wires. So we can feed this T into a zkSNARK, but we also need to prove that it actually represents a ROM. That is, if an address is queried twice, it will always return the same value, right? Nothing is changing from underneath the nose of the prover or the verifier. We call this property consistency, and that's all that means. If you query an address twice, you get the same value. We can phrase this slightly differently. We'll see why in a second. Let's sort the trace by address. Let's call this A. So it just means that the addresses are monotonically increasing. So consistency is the same thing as saying that every run of identical addresses in A is also a run of identical values. This shouldn't be too surprising. We're going to see why we prefer this in a second. Let's look at what the prover now does. First, it computes all of the shared wires and makes the ROM table just as before. It splits the time and address sorted traces into individual chunks called subtraces. And then it farms out subproving just as before, but this time also passing the relevant subtrace to each individual prover. Each subcircuit prover has to prove the well-formedness of the subtraces. So that means it has to prove that the address sorted one actually is address sorted, so it has to check the sortedness property. And secondly, it also has to check the consistency property. And then finally, you have to show that A is equivalent to T. These two traces are actually the same thing. In other words, they are permutations of each other. And then finally, you aggregate all of the proofs. So now we can answer the question of why A exists. The sortedness and consistency checks here are entirely local, right? That means it's a property that can be independently checked for each individual subtrace on different machines. And if each subtrace is individually sorted and individually consistent, then the full trace is sorted and the full trace is consistent. So these local checks imply a global property, and you get to do them in parallel. So that's why we sort things. For the keen-eyed of you, you'll notice that this is almost true, but not exactly true. We'll get to that. But more importantly, we're going to address the permutation question. These traces might get pretty big, so how can you distribute that, right? So how can you prove that these things are permutations of each other in a distributed way? So we're almost done here. Showing that A is a permutation of T is the same thing as showing that the polynomial whose roots are the element of A equals the polynomial whose roots are the elements of T. The intuition here is that multiplication doesn't care about order, so these things should be equal regardless of the order that they appear in the trace. Furthermore, we know that we can do efficient polynomial equality checks just by checking at a uniformly selected point. This is called the Schwartz-Zippel lemma. So here's what we'll do. We're going to randomly select a point R and then incrementally evaluate T of R and A of R. And so we're going to do this incrementally by just multiplying into some running evaluations, right? The current evaluation is equal to the previous evaluation times all of the terms that pertain to this particular subcircuit. So importantly, this is local. Finally, since this is a non-interactive proof, we need a way of selecting R that can't be gamed by the prover. For this, we use a commit and prove zkSNARK, specifically commit and prove Groth16. We commit to all of our witnesses, i.e. the subtraces. We then do an inner pairing commitment over those commitments, so we commit to the commitments. And then we hash that, and that is our challenge. And that is what we use for all of the intermediate evaluations. And like I said, these incremental evaluations, they're indexed by subtraces, so each individual prover can just run this on their own subtrace independently of everyone else, and the commitments are also based on the subtrace. So all of these run entirely locally. So we're kind of done. But we have one issue. How can you incrementally update the eval? Right? Doesn't that require passing information between individual subcircuit provers? And similarly, for sorting and consistency of A, you need to check all adjacent entries, right? Even those that might occur in different subtraces and hence exist on different machines. We said that we don't want internode communication, so how can you do this? Well, since these accesses are known in advance and do not change, this is equivalently a problem of achieving globally accessible read-only memory for a zkSNARK prover. In other words, this is a ROM problem. Wait, we're solving ROM by using ROM. How does that work? We're just gonna use a Merkle tree here. This is fine. The reason why we can use a Merkle tree here and just bottom out is, yes, it's the more expensive option, but it's a much cheaper problem than before because we only have to do a handful of fetches for each subcircuit. So not for the entire memory chase, but each individual subcircuit only needs to fetch like 3 or 4 elements from the Merkle tree. So this can be concretely very small. So recapping the protocol, we have a coordinator that sends all of the subtraces. It calculates the trace and sorts it, and it sends the subtraces to each of the individual worker nodes. The workers individually commit to their traces and send back the commitments, which are then aggregated and then hashed to compute the challenge. The challenge is then sent to the workers. The workers finish up their proof. They send it to the coordinator, and the coordinator aggregates them. So let's look at benchmarks. We wrote a large circuit that computes the root of the Merkle tree. Each individual node of the tree is its own subcircuit. It takes the shared wires from its 2 children and outputs a shared wire to its parent. In our experiments, we scaled up to 2 to the 35 constraints and 4,096 cores. We were able to run our largest experiment in just 17 minutes. And more importantly, we're able to show that our throughput scales linearly in the number of cores. Importantly, in other words, this is embarrassingly parallel. Also, the communication overhead is concretely small. It's dominated by the size of the traces. And also, verification is concretely fast. Our largest proof for the record-breaking circuit is 64 kilobytes, and it took 83 milliseconds to verify. For comparison, a single pairing operation on one of these machines takes about 2 to 3 milliseconds. As a bonus, we also realized that the ability to break up a circuit into subcircuits means that you can prove them serially and save memory that way. So we allocated just 1 core and 4 gigabytes of RAM and ran large circuits on that. It was not fast. But no circuit on this graph could have been proved using a single monolithic Groth16 prover. It would have run out of memory immediately. So this is actually still pretty cool. So in conclusion, HEKATON is an embarrassingly parallel zkSNARK prover. We built this using circuit partitioning, ROM, commit and prove Groth16, and we have an optimized aggregation mechanism for that. It scales linearly, so it's embarrassingly parallel, and it's also just concretely fast to prove and verify. For future work, we want to extend this to other proof systems and also implement lookup tables. And with that, I will take questions.
I have a question. So, is it technically linear time if you have the sorting step, because it's log in at the coordination nodes?
Oh yeah. So sorry. The proving time is probably not linear because of that. What I mean by linear here is that given it's a statement of parallelism. Like given a certain amount of work, if I throw throw twice as many cores at it, it's going to complete. It's that more expensive part is going to complete in twice the amount of time. The sorting part is by far cheaper than everything else, so it's all dominated by the linear part.
A little bit of intuition of how large the sorting portion is. Is it like less than 10%, less than 5%?
Much less than 5%. It's
got it.
Yeah, maybe like 1% or something like that.
Awesome. Any questions from the audience?
I thought your example running this on low memory machines was like pretty interesting. Have you thought through any of like the implications and like the applications of that?
Yeah. So one thing, I don't think it's in the paper, but I was excited by this. There's a protocol called MLS that's used for end-to-end encrypted messaging, and part of MLS involves sending a key package to different parts of a tree. So you have to take this key and encrypt it multiple times to different individuals. And so one thing that you could do if you wanted to tank the entire session is take different keys, encrypt it to the different people, and now everyone thinks that a different key is being used in the scheme. So one interesting thing here is, can you do a zero knowledge proof that all of these keys are actually the same, right, without revealing what the key is itself? There's been some work into this, but this can get to be a pretty large computation because this is HKDF of HKDF of HKDF, right? So if you can do this serially using low memory provers, then like maybe this can run on a phone. So that's kind of interesting to me.
No takers? Oh.
Did you look into something like Jolt where you don't have to do sorting again? The memory check from there, which was from Bloom et al. I don't remember when that was from. But they have a permutation check without sorting.
Oh, no, I didn't even know that that existed. You said it's called Jolt? Yeah, okay, I'll read Jolt. Awesome, thank you.
Yeah, also probably there's a lot of industry work where similar things happening where you break down the computation. Anyways, let's thank our speaker again.